Awesome. So I'm going to talk about green infrastructure for reducing energy and air quality impacts in the Chicago region. I'd like to acknowledge a few of the co-authors who are already here in the audience. And I represent University of Illinois and Argonne National Lab. And I'm going to talk about a few of the projects that we are involved in and what are we learning from those in a very broad sense.
Yeah.
Okay. So if you think about urban systems are really multi-scale, interdependent, social, natural, and engineered complex systems. I always like to show this video of infrared camera showing Chicago downtown area that the urban areas where we live in are really hot, and also the communities that that live in those urban areas also contribute to heat. We are around 50% of populations living in urban areas, or by 2068, 2070, almost 17% more increase would happen. So we are putting a lot more stress over urban areas. And as previously mentioned, these DOE IFLs are one of the approaches where we are trying to understand how do we address the vulnerabilities these areas are having. Uh, this one. Okay. So the challenges in general for any urban area are related to high heat, poor air quality, lack of green spaces, open spaces for recreation and physical activity. And you can think about much more, but in general, those are the things. If you look at Chicago area, you can think this is the cross section that we have put here. We have Lake Michigan, which is like an ocean, but it's a freshwater lake. And then we have skyscrapers, built environment. We have industry, and then the Corn Belt. So there are a lot of processes that are going on, even though the terrain looks very, very simple and flat, but the complexities are a lot more there. We have high energy stress, high urban heating, and poor air quality. So overall, the environment is very stressed. Overall, the environment is very stressed. And what we really wish for, and what my urban utopia is, that we want an environment which has low energy stress, less air quality issues, and also a lot more green infrastructure. When I talk about green infrastructure, I mean green cool roofs, even also technological solutions like photovoltaics. Overall, what it will lead to is better quality of life. You can see here, people are not happy, they're distressed, but now the people are happy. So I just wanted to add people there. Okay, so if you think about in a broad sense, urban issues, 40% of the world energy use and 40% of the emission comes from urban environments. It is said that 900 billion square feet of built space will be built or rebuilt over the next 2 decades. So if you look just for Chicago, around 72% of greenhouse gas emissions come from building, 25% from transportation, and rest from others. It's not only the greenhouse gas emissions, but also we have air quality issues related to particulate matter and ozone. So we have issues both related to greenhouse gas emissions as well as pollutants. If you look with respect to plants and trees and urban vegetation, trees in Chicago are not distributed evenly and equitably like in other regions as well. Chicago has around 23% tree canopy, which is far below the national average of 27%. Chicago region itself, so I was talking about Chicago as a region, but now city of Chicago has 16%, far less. This is city of Chicago right here. It has 16%, which varies from 10 to 46%. So there's a lot of inequity within the city of Chicago. So 2 years back, city started a plan for tree equity, which promised to invest around 46 million. So and planting around 75,000 trees. So they have planted around 18,000 trees as of now within a year, and I think the plan has been successful. So if we are thinking about solutions, you can think of these as green rooftops that you have heard a lot of talks, urban forests, permeable pavements, photovoltaic roofs, electric cars, and so on, and even the cool roofs. We we worked on a policy document where we created a Chicago region climate action plan, and this was unique in itself because generally climate action plans are created for cities, but this was for a region, and so that what can we learn from 275 municipalities in the Chicago region? So we have documented these things, that what kind of solutions that the region can have so that we can have inclusive growth. So I'm going to talk to you about these solutions. I'm just giving a broad overview of kind of framework that we use, but this doesn't apply to all the simulation results that I'm going to show you, but just a depiction of some kind of modeling exercise that we do. So we run weather research and forecasting model and downscale that to 1 kilometer resolution. This is just showing the older style of having urban land use classification with 3 land use classification. So we spin up the model for 1 or 2 days, and then do the nested downscaling in steps of 3 up till going to 1 kilometer. So here are the results from green and cool roofs, and I think everyone knows how green roofs and cool roofs works. Green roofs works on the principle of conversion of sensibility to latent heat, and cool roofs use reflection to cool down the buildings. So this the simulation shows that if we aggressively use green roofs in the Chicago area, we could reduce the temperature up to 7 to 8 degrees Celsius. This is a lot more decrease than that we can have. The decrease will not only happen on the surface or roof surface, but will also decrease the temperatures within the boundary layer. So we could decrease the temperature up to 2 to 3 kilometers in the boundary layer. So, and this is not rocket science. We would know that if you put green infrastructure, it would reduce temperature. Just putting it out and saying, okay, how much is that contribution? But what is important to address is what are the interplays when we look at transport processes and photochemistry processes when you implement green infrastructure solutions. And I'll give you one example here. Uh, we published this study in 2018. It was well cited and well received, where people built up on that and said, okay, it reduces the PBL height and it would have impacts on air quality. But to the best of my knowledge, no one had tried to look at air quality implications thereafter. So what we did is we ran the roof cam simulations, including urban areas, and tried to see, okay, validate the hypothesis of what happens to air quality. So here you can see, if you're looking at the cross section A to B, if you have conventional roofs, the ozone and the PBL height is very high, and you can see a lot of good distribution of ozone in some sense. But when you use aggressive mitigation strategy like green roof, the PBL suppresses, and you see a lot more ozone. So what it tells us that you can't aggressively use these mitigation strategies. Uh, in a very simple words, if I explain, if you aggressively use a mitigation strategy, it is similar to uh, reducing heat on a pan, and you are having less convection. And because we have the lake, you are also having less advection because the pressure gradient has changed. So, so what it means that of course we need to use these, but how do we plan solutions? So that's what I'm going to talk about next. Before that, so we also looked at air quality implications. Uh, so the ozone concentration during daytime, concentrations were higher at the city center, and they were lower as we went further, and it was opposite during nighttime. So this is 8-hour ozone, which is a standard to use. So when we look at green infrastructure solutions at scale, it matters. So this is at really hyperlocal scales because we can't really implement green solutions at a city scale in those hypothetical studies. So we have excellent LiDAR maps over 1 feet resolution. This is just showing the cross section over this area. And with this, you can even resolve even the light poles in the buildings. So we can use this type of data sets in the previous studies, for example, which were looking at pedestrian level thermal comfort to really use the data set and calculate those numbers. If I can, this was the animation which was showed yesterday. So we use this type of data sets with observations to really depict what happens at city scale, at hyperlocal scales. Now, you can use these simulation results to identify where to put green roofs. Okay, so you don't have to put them throughout the city, but you can do targeted experiments. An example, if you zoom out, is this one, where we can work with the city to really tell the city, okay, this is where you should not invest in trees, but these could be the possible places, like identifying really targeted examples. Okay. So next is urban vegetation. We talked about pollutants. So in addition, we're also very interested in CO2, right? How does greenhouse gas emissions are related to urban areas? So we did some study where we are looking at biogenic emissions. How does plants and trees and urban vegetation address the CO2 issues. So we calculated that into different scenarios and looked at how the net ecosystem exchange would look like for Chicago. We have also developed an environmental benefit score. There's a paper under review, and we can share that for more details. I'll give the last example because I don't have time on photovoltaic roofs. So we are building up on this study based on Zonotto's article that came in JGR Atmosphere, where we are looking at rooftop photovoltaic potential, and then calculating AC consumptions, also converting that into how much would be the CO2 offset. This is important because at times when we talk to communities, cities, they don't understand the language of how much would be the effect with respect to kilowatt hours. How can we convert into a language where the policymakers can understand? Also, at the same time, where communities can understand how many cars would be off if we do that. So I'd like to just finish my talk by giving these takeaways that we need careful consideration to address the co-benefits of cooling and carbon reduction using urban vegetation, as well as impact on air quality within the urban boundary layer. These solutions can provide energy savings, reduce greenhouse gas emissions, and promote clean energy production. We can use hyperlocal urban features that I just showed to downscale temperature predictions to street scale, and also design MODEX approaches, which is the model experiment where we use observations, array of things observations that I showed previously, and the models to design solutions that are really hyperlocal scales. And also that way we can target solutions for vulnerable areas. And a key message is we can't aggressively use a mitigation strategy. So how can we use a mix of solutions, but finding that mix of solutions in targeted locations where we can have really good mixing the atmosphere, but also taking advantage of those approaches. Thank you.
Back to the back row here.
Thanks for the great presentation. I have a simple question about what type of vegetation you have used there.
What type of vegetation we used for?
Trees like evergreen.
Yeah.
Did you select any specific?
I think for green roofs we use sedum. I think that's the one that is implemented in the WRF mode, WRF model. We have not played around with the vegetation types, but we use what is available in the WRF model.
Okay, because my understanding that vegetation will contribute to natural emissions in the future, biogenic emissions. And thinking about 20, 30, 40 years from now, most impact on climate will be coming from natural and biogenic sources, not from anthropogenic sources. So definitely, if we don't take into consideration those aspects, that needs to be.
Yeah. So that is why we tried to do a follow-up study where we are looking at the biogenic emissions. So to see how the trees, the grass on the lawn and shrubs contribute to heating as well as to CO2 sequestration. So and our future work we'd like to now couple and see how much CO2 sequestration in different scenarios, say heat waves or doing a lot of extra irrigation, can lead to changes in biogenic emission and also the relationship with heat and air quality in general.
You know, I don't want to hold the meeting because all the others, they might have other questions. But then you need to think about what chemical mechanism you need to use within your air quality models. If you use water, doesn't have a chemistry like chemistry, then you have to move to CIEMAT or any other models. Then you have to get chemical mechanisms that require to be looked at.
Yeah, we have a big field campaign and projects going on in the Chicago area. So I think we'll get lessons learned from observation sites so that we can make sure our models do the job to capture them. If not, we'll go to other sources. Thank you.
So you use a mesoscale model that you use at subgrid scale. You could also use a microscale CFD-based model. So I would like to hear your opinion. I know you would say it's much faster, but there should be other motivation why you use a laser scale model.
So we use CFD-based models as well. They might, I don't know if there are other talks.
I talk a lot about it tomorrow.
So yes. So I think there was a talk with, where our colleague Peiyuan talked about yesterday. So we are talking about this multi-scale modeling approach where we want to use these models at different scales based on the advantages that they offer, and also leveraging where the physics starts failing, the machine learning algorithms and the observations that we have to learn from that so that we can create new models moving on after these campaigns and projects end.
I start sense. I'm not sure what the correlation between ozone, what you mentioned, and roof color change and boundary layer height will be so simple. Because ozone is secondary pollutants and precursors are ruling. And probably maximum you'll have outside the city. So impact of roof will be, it could be opposite.
Yeah, so
For example, for this COVID period, we analyzed for different cities around the world, and for most of pollutants, of course, it was reducing during the this period, but for ozone in some cities it was increasing.
Yeah, so I think those simulation results are without, frankly, comparison with observations, and we are going to do those comparisons. But I think the idea was we have established a mechanism to address them, and then maybe next year, maybe at AG or AMS, we are going to talk about how do we validate those results. But we looked at particulate matter too. So I think the suppression of boundary layer kind of made the pollutants really close to the near surface, and that was not helpful. But however, if you use
results, definitely yes, but not always for ozone.
yeah,
Chicago does some unique meteorology when it comes to ozone and the sources as well.
Absolutely.
and also it depends on what is it, what photochemistry or high pressures are being developed over the area. If you have a high pressure, then it could lead to clear skies, for example, and then clear skies could activate the photochemistry, and then you have extra production of ozone. Or you could have other mechanisms where pollutants get trapped somehow because the advection somehow stops because of it's a very quiescent conditions if there's no large scale flow, and that could create that too. So as Scott's mentioned, there are a lot of competing factors that go in there. So yeah, we'll investigate with very carefully though.
The field campaign, the Aroma and Stacks field campaign that recently flew over Chicago, I'll talk really brief about that tomorrow, but that's going to give some outstanding data to really look at this with profiles of ozone.
And I think there's one last question in the back.
I think Scott actually mentioned that part, or Scott Alexander. So what I was trying to say about that, the source and sinks, basically that, we think about the boundary layer is actually diluting the pollutants like PM 2.5, but it's basically at the cost of the intrusion of the free atmosphere, and the free atmosphere decides what will happen in the boundary layer. So I think Scott mentioned that the ozone profile will give you the opposite scenario. Carbon dioxide profile will give you the opposite physics, because in the winter time, carbon dioxide concentration is higher in the, like in the free atmosphere versus the boundary in the summertime. So those splits will come, right? And so it's not necessarily traditional that boundary layer will grow, pollutants will be lower. I think we need to get to the free atmosphere intrusion into that part, and that I think work can.
Yes, so I think those are detailed in next steps. For example, how do we assimilate NASA satellite data, and then making sure are we able to capture those, and then also using the aircraft campaigns. We are just building up on these, so hopefully when we have those much more interesting events moving on, we can try to separate those and maybe come up with a catalog of, for this event, for this type of things, something like this happens, so the communities and the city can take an action along those lines. So yeah, we'd like to do something like that, so that a lot of these questions that we are trying to answer are driven by what community needs, and then going from that stage and looking at how can science support them and address them thereafter.
All right, we have reached the official end of the session. So one final applause for Ashish and all.